So we have a little problem to start out with today. See if you can remember how we did these. I probably shouldn't hum. So who remembers the empirical rule? Andrea, do you remember the empirical rule?
Yes, but not like memorized.
That's okay.
Okay.
Here it is. The empirical rule says for normally distributed data, 68, we've been saying about 68% is within one standard deviation, about 95% is within two, almost all is within three. This particular chart is a little bit more precise with those abouts, and we will actually learn how to get super precise with those abouts today and tomorrow. By implication, because the normal distribution is nice and symmetric, we've done this before, kind of gone in and figured out that these two were about 34%, half the 38, subtracted the 68 from the 95, figured out about what the space between the first and second standard deviation was, did the same thing between the second and third standard deviation. So we've broken this empirical rule down into pieces before. So given this empirical rule, either the more general 68, 95, 99.7, or this a little bit more accurate one, trying to answer this question of what's between 12 and 14, well, 12 and 14 is between the first standard deviation and the second standard deviation above the mean. Hence, there's z-scores would be a nice 1 and 2. Remember how to find z-scores? Z-scores are our value minus our mean divided by our standard deviation. If it was a population, we would say x minus mu over sigma as opposed to s and x bar, but either way, it's mean and standard deviation. So that z-score for the 12 would be 12 minus the 10 over 2, which is 2 over 2, which is 1. The z-score for the 14 would be 14 minus 10 over 2, which would be 4 over 2, which is 2. So that's where those z-scores are coming from, essentially. So if we want to know what the area is between that 12 and 14, luckily that 12 and 14 are even cuts of our standard deviations. So we could use our empirical rule. And again, this chart has already broken that down. So we get a nice 13.6. I think it's 13.5 if you use the 6895 instead, but this one's a little bit more accurate. So 13.6%. Or because this question asked as a proportion, the proportion is 0.136. If you said the proportion was 13.6%, I wouldn't argue with you. But by habit, if it asks for a proportion, it should be in decimal. If it asks for a percentage, give it in percentage. And then you can take your empirical rule graphic here, get rid of it, so people just think you just did that off the top of your head. So it's been a little while since we've worked with that empirical rule. And whether you remember all the percentages or not, you remember working with that tool and doing problems like these, I hope. Yes? Now, the trouble with this problem, or the problems like this that we've done so far, is we have been very restricted to them only asking us questions that were very nice, that were exactly values of the standard deviation. But that's certainly not always going to happen. So what happens if somebody asks us to find, say, the proportion of values? Oh, how about we just say less than 11? Now this brings up a couple of issues. If it had said less than 10, well, less than 10 would be from 10 down. Well, that would be half. So we could have done that. If it said from 12 down, okay, we'd have been able to use the empirical rule to say there's 50% here, and knowing that there's 34% here, we could have said 84%. So we could have used the empirical rule for 12 and down. But 11 has a problem. 11 is not an exact standard deviation. It's not exactly 1 or 2 or 3 standard deviations. And our empirical rule isn't that precise. Our empirical rule is for whole values of standard deviations. So we need a more dramatic tool. We need something that's a little bit more complete than just, well, what happens at 1 standard deviation? What happens at 2 standard deviations? What happens at 3? We need a tool that will allow us to talk not only about half standard deviations, but really any little break here. If we wanted to go, say, what's less than 10.3, we should be able to have a tool that tells us that. So today we want to start talking about those tools. So if we want to find the proportion, or sorry, the probability of our value being less than 11, we're going to do that by first turning that from a value into a z-score. Because I don't want to have to figure out a new set of proportions for every different values we have. We can turn all values into a z-score argument, and then everything we know about the z-scores can be applied to any other data set. So we'd have to figure out what the z-score is for 11. So I'm going to go off. Z-score for 11 would be 11 minus 10 over 2, which would be 1 over 2, which would be a half. So the probability of that z-score being less than 1/2. I'm actually going to put that in decimal form. I hate to do that, but it's going to be handier for us today. Now, this process of turning all of our data into Z data instead of raw data is called standardization. We're standardizing this data. Allows us to turn any data into the standard z-score z-score distribution that we see here. So often when we look at these distributions, we don't even look at the data on them. All we ever see sometimes is just this, where the mean is 0, because the mean has a z-score of 0. And this is listed in terms of z-scores instead of raw data. So that's just standardizing our curve. So all curves essentially become this standard curve. So if we wanted to find the probability or the proportion of this data that has a z-score less than 0.5, well, that z-score of 0.5 is going to live right there. So we essentially want to know what proportion is down here. Now, how are we going to do that? Well, luckily, we don't have to directly calculate that. But a couple pieces of information. One, this normally distributed curve, this graph here, is referred to as a density curve. And all that means is that the actual physical area under this curve is 1. So if you found the area of everything under that curve all the way out to a z-score of 4 or 5 or 6, all the way out, you know, the little tiny areas that we can't even see under the curve after 3. If you measured that area, it would add up to an area of 1. So we're not just looking for the proportion under this curve, we're actually looking for its actual area. So looking for its actual area means we can bring in a bunch of tools from things like geometry, and more importantly, a tool from calculus. The very nice tool from calculus that allows us to find areas under curves. But we don't know calculus. And it's actually a fairly tough calculus question to do, even if we wanted to. It's a pretty brutal one, actually. At the end of Calc 2, I make students go through and figure out all these values. But it's not an easy thing to do. So we want to let or make somebody else do it for us. And those somebody else's are going to be our 3 sources for this data. Just like yesterday, we talked about the 3 places that we could get binomial information from. There are going to be 3 places we're going to be able to get these areas from. The second 2 are going to be the same as they were yesterday, Excel or the calculator. We will have a tool, we'll talk about them tomorrow, to be able to ask the calculator, hey, what is the area under the curve from this point down? But the first tool I want to start with is called a z-score table. You will find a z-score table in your textbook. There should be one in this, both in this section and a nice big one, either at the back of your textbook or the beginning of your textbook. I can't remember. I think it's the end. There's a bunch of tables at the end of your textbook. But what that table will look like, and these are very common, you'll see them all over the place. You go online and search Like go to Google and search for a z-score table, and you will see all kinds of z-score tables. But what they look like is this. A massive table of values. And what this table of values is it is the area under these curves from a z-score downward. So if we wanted to know, like for our particular problem, what is the proportion under the curve under a z-score of 0.5, we would just go to our z-score table and look for 0.5. Now, all of these z's are negative, so we want a positive. So we go over here. Here is positive 0.5. Now, these are hundredths place, so this is 0.5 tenths, but that's 0.50, 0.51, 0.52, 0.53, 0.54, and so on. We just want the 0.50. So that number there on our chart, somebody did the calculus work and figured out what the area was and put it on the chart. So our area, our proportion is 0.6915. So we simply go back to our problem. This pink area is 0.6915, if I remembered that value correctly. 6915, yep. So what proportion of values are less than 11? Well, 69.15% of values are less than 11. So instead of having to use the empirical rule, that chart, this chart, is basically a giant empirical rule that instead of being broken up by 1, 2, and 3 standard deviations, it's broken up by any 1/100th of a standard deviation. A lot more information on it. You're certainly not memorizing this in any stretch of the imagination, but it allows us to answer a vast amount of more detailed questions. Excuse me. If we wanted to be more detailed than these hundredths, okay, the calculator and Excel can give us even more accuracy. So today we're going to stick with using the table because I think it gives us a nice feel for what we're doing, and you'll use your tables a lot. But then tomorrow we'll start looking at, okay, how do we ask the calculator these same questions? Now I want to do another example real quick, but questions about that example before we do that. I do recommend anytime we do these to draw a nice diagram. I'm just copying and pasting a nice graph there. Are all z-score tables the same? Yes and no. Essentially, no. Why are there so many kinds? Style, mostly. You'll see 2 or 3 major different types. The basic type, and this is the type you'll see for the vast majority of them. The basic type gives you from the z-score you're asking about downward. It's essentially the same as that a cumulative argument that we talked about yesterday. One of the things that people don't like about the chart set up this way is it has to have all of the negatives and all of the positives, which makes for a big chart. You will see some people, some charts, that instead of having the diagram, they almost always have these pictures with them that tell you what they're doing. Some of them you'll see the picture goes like that. It goes from halfway upward. So it goes from some given value down to half. Well, since we always know that that bottom half is 50%, if we know this piece, we can just add 50%. It does make for a shorter chart in a weird way, but it's essentially the same. It's just whether it's giving us the whole thing or just half of the thing. So those are the two main types you'll see. We will stick with the full one, but there's just a couple of different styles, mostly depending on what you're looking for from your data. But this is by far the most common. Hopefully that helps. So let's just, for a nice kind of raw data example, let's say we are given normally distributed data with, we're told a mean. Let's say that mean is 43 and a standard deviation of 8. And we want to find the proportion. Let's stick with a less than. So let's say less than. So the proportion of values less than 50. So if we're going to use a standard curve like this, our first job is to find that z-score for our 50. The z-score for our 50 is going to be 50 minus our mean divided by our standard deviation, which would be what, 7/8. So that puts the 50 roughly here at a z-score of 7/8. Thus, we want less than that 50, so less than that 7/8. So we essentially want everything from that point down. So we're looking for, hey, what proportion of the data is down here? Now it'd be nice to know what that z-score is as a decimal value, because that's what's on our chart. So the decimal value for 7/8 is what, 0.875, I think. Here's a 0 plus 7/8, because that's when we standardize it, the z-score for 50, sorry, the z-score for 43 would be 0. So the z-score for 50 is 7/8. So I'm not sure why you have z plus 7/8 there, Alan. Let me know. Okay. So that z-score for 50 is 8.75. We want to know what's below that z-score of 8.75. And again, that's luckily what our chart tells us directly. So we just need to get as close as we can to 0.875. So we go to our chart. Pull us over a little bit. So 0.875, there is 0.8, 0.8, 0, 1, 2, 3, 4, 5, 6, 7. So 0.8. So that would be for 0.87. And again, our chart only goes up to the hundredths. So our 0.875. If we wanted to round that to 0.88, that would seem reasonable. So if we wanted to go 0.88, we'd actually be using that one. So 8106. So we go back to our problem. The proportion of z-scores less than 0.875 is, I already forgot. It was right there. 81.6, right? 8106. Okay. 8106. So that means, in answer to our question, the proportion of our values that are less than 50 is that same 0.8106, or a little more than 81% of our data is less than 50. So this big yellow area here has an area of 0.8106. Is that horrible? I mean, we're going to try to make it horrible by the time we're done today, but yes, it's horrible.
So does that mean with this one, like the last problem, it would be the area under the curve of a z-score of 0.875 would be that 0.8106?
Yep.
Okay. And it's percent. Do we put it in percentages or just leave it as decimal?
I would tend to leave it as decimals unless you're asked for percentages. But if somebody, if somebody was saying, what's the proportion, and you said 81.06%, that would be perfectly reasonable.
Okay. Okay.
We're going to tend to use the decimals by default. But in conversation, particularly if you're writing them in sentences, it's really common to just say it in percentage. But mostly I want you guys to be comfortable either way. And the best way I can make you guys comfortable either way is kind of pushing the proportion language, because the percent language we're usually comfortable with. But if I was going to write this, if this was like, the weight in grams of something I'm trying to manufacture, saying, 81.06% of them weigh less than 50 grams would be perfectly reasonable method of expressing it. So let's say with the same data, so that same mean of 43 and standard deviation of 8, let's say we wanted to find the proportion, or you could say percentage, of data. I'm going to stick with less than for another problem. Less than, how far do I want to go here? How about 25? So we could write that as the proportion of x's less than 25. You could also think about this, by the way, if somebody asked, what's the probability if we grabbed a random thing out of here, what's the probability that its value would be less than 25? So lots of different ways these questions will sound. So what's the first thing we have to do with that 25?
Find the z-score.
Find the z-score, standardize it. Don't panic. Don't panic, Alan. The first thing we need to do is standardize it so we could use our tool. So the z-score for 25 minus 43 over 8. So we're essentially, again, asking how many standard deviations below the mean is 25? So that's going to be what, negative 18?
Negative 2.25.
Or negative 2.25. So that's way down here. Z-score, negative 2.25. Actually, I guess it's more here. So we're only finding this little area down there. So we should expect it to be fairly small. So, well, how do we find it? Well, we go look for that in our z-score chart or table. Go to our z-score table. We want a negative 2.25. It's negative, so we're going to be over here. Negative 2.2. So there's our negative 2.2. We need 2.25, so that's 2.20, 2, 3, 4, 5. This is kind of a weird table that you need both the side and the top to give you where you are. It takes a little while to get used to that. But that is negative 2.25. So 0, 1, 2, 2. Very small, as we expected. 0, 1, 2, 2. So that little thing, 0.0122, little tiny area down there. So the probability that the proportion of z-scores less than negative 2.25, that's what we found, 0.0122, but that is going to be equal to the probability of x values less than 25. The z-score argument is just the standardized version. So 0.0122. So what proportion of these things that we're manufacturing are going to be less than 25 grams? Well, only a little more than 1% of them are going to be less than 25 grams. Got any questions you can ask about that before I start throwing a wrench in it? That is the fun part. So let's say we just, I don't want to modify this question a lot, but what about, same data, then we're going to look at different data in a minute, but no, it might seem reasonable, but panicking never helped anybody. How about what proportion or what percentage portion of the data is between, say, 50 and 25. And we start talking about it in terms of grams, so let's stick with that. So what is the proportion that is bigger than 25, but less than 50? Well, we've already messed with 25 and 50, so we already know there's z-scores. So what's the proportion between the z-score for 25 and the z-score for 50? So the z-score for 25 was negative 2.25. So what proportion of z-scores are between that negative 2.25 and 0.875? Now, we know it should be a fair amount because, 50 was over here, 25 was over here. So the big chunk of our data is between those two. Well, if we know that from 50 down was let me go black. If we knew from 50 down was 0.8106, and we know from 25 down was 0.0122, so we know all of that yellow was 0.8106, but the purple part, turned kind of brown in between, was 0.0122. If we want to find just what's left between here and here, just the part in between, what can we do with those two values to find what's area is in between them? We can subtract. Yeah. And Alan, that's sort of what you did. You took the 50 minus the 25 and said 25. We're not trying to subtract their values. We're trying to subtract their proportions. So find their proportions and subtract those. And that's going to be what? 0.79. Oh, something. Help me out. You guys have calculators, right? Andrea will come to my rescue.
Uh, 0.7984.
84.
I got the same for that too.
Cool. So just between that 25 and 50 is 79.84% of our data. So sure, if we'd been asked this question from the beginning, we'd have to go, find the 50, find the 25 like we did, and then subtract them. But if we know how to find the 50, know how to find the 25, we can do that. Questions about that before we look at a different one? I just want to look at different examples, different ways this could be expressed today. Hi, Micah. Do draw these diagrams. Makes a difference. So again, we're going to be given normally distributed data. We'll be given a mean and a standard deviation. Oops, no bar on the standard deviation. And these could really be almost anything reasonable. How about, oh, I don't know, 20 and 3. So if we were to list out our table in terms of data, that would be a 20, a 23, a 26, and a 29, a 17, a 14, and an 11. We're just looking at the normal curve. So the normal curve is looking at it in terms of its z-score. So instead of looking at this as 23, we're looking at it as 1 standard deviation from the mean, 2 standard deviations, 3 standard deviations. 20 is no standard deviations from the mean. And the negatives are just below the mean. So that's us standardizing the curve. That's why we turn everything into z-scores, because that way we've turned everything into the same measure. So what can we make this data? A average of 20, let's say people. Let's say we're measuring how many people come to our parties. I don't know how many people come to parties. I don't go to parties. But say we have an average of 20 people come to these, I don't want to say parties, how about meetings? An average of 20 people come to these meetings with a standard deviation of 3 people. So I'm going to put this in terms of a probability. What is the probability that at least, everybody's favorite phrase, that at least, let's say 18 people come to the meeting? Now we could say what proportion of meetings have at least 18. We could say what percentage of our data is at least 18. This is our termed as a probability question. It's all the same question. So just like before, our first job is going to be to figure out where that 18 lives on our curve. Well, that 18 is certainly less than the 20, so it's going to be a negative on the negative side. 18 is less than 1 standard deviation, so it's going to be somewhere around there. And I'd like to know what that z-score actually is so we can use our tools to look it up. Some of the tools we learn later, we won't actually need the z-score. The computer will find it for us. But for right now, it's good for us. So 18 minus 20 over 3, that's 2/3, or in decimals, 0.6 repeating. So I'm just going to go 6/7. It doesn't help me to go any further than the hundredths place because that's as far as our chart goes for z-scores. So, okay, off to the z-score table with 0.67. Before I do that, any questions? You guys are being kind of quiet today. Any questions on where that z-score came from?
Yeah, sorry. Can you explain that one more time?
So the job of the z-score is to tell us how many standard deviations from the mean we are, right? Oh,
Right.
I'm glad you asked because that z-score is actually wrong. So how far are we from the mean? Well, 18 is pretty close to that 20. 1 standard deviation off would be 3 less, right? This is not quite 1 standard deviation below. So we're asking how many standard deviations below it is. So the first thing we figure out is, well, how far off of the mean is it? And it's -2, not +2. It's -2 values from the mean. How many standard deviations is that? Well, it's negative. That should have been a negative. 2/3 of a standard deviation from the mean. And that's our z-score, is our value minus our mean. How far is it from the mean in terms of standard deviations?
Okay,
But
thank
thank
you.
you, Olivia. That absolutely should have been negative.
Okay, thank you.
So negative 0.67. So if we jump over to our chart, negative 0.67, it's going to be on the negatives. There's our negative 0.6. And there's our 7. So our negative 0.67 is right there. So 2514. Jump back before I forget it. 2514. Now, our z-score table does naturally tell us below. So that 2514 is the proportion below our given z-score. So that's what our chart has told us. Is that number the number we want? Alan, you said no. Negative, because it's under the mean. It's not what we want. We want at least 18. At least 18 means 18 or more. So we actually want this upper area, not the lower area. Oh no, how are we going to deal with that? Tessa, Olivia, Andrea, Micah, any thoughts? Our table gives us below and we want above.
Wait, so are you asking that we're trying to find everything that's in the red or in the yellow?
Well, our table told us everything that's in the red, but the
Right.
question asked for what's in the yellow. So the question is asking at least 18, that's 18 or more. So we want this. The table
Can we just
gave us
subtract that
this.
number with the red?
From what?
What's in the yellow? Or no?
But it's from 18.
As long as we remember that the whole thing is 1, right?
Right.
Yes, we can subtract it from the 1. So 1 minus the 0.2514.
And then we'll get that answer.
Yep. Do be careful, Alan. You've fallen into one of the good traps. We're not subtracting the z-score from 1. So it's not the 0.67 subtracted from 100. It's the area, the 2514, subtracted from the 100% area. So don't subtract your z-scores. Subtract your proportions. Very common trap to fall into. So that would be what, 74 or 0.7486. So that means this is 0.7486. So same kind of logic from our binomial distributions. If we want the above portion, our tool doesn't like to give us the above portion. Our tools will like to give us the below section. So subtract it from 1.
And then that's our answer, right?
And that's your answer. What's the probability that at least 18 people will show up? Now, if on average 20 people show up, we'd expect it to be more than half the time at least 18 people would show up. How much more than half the time? Well, 74.86% of the time. At least 18 will show. I want to give you guys one and kind of give you some time to play with it and see what you guys come up with. How hard to make this one though? Hard level 1, 2, or 3?
2,
2?
1.
Put in the middle.
1.5.
Not a 3 though. All right. So let's say
0.5.
0.5. It wasn't an option. Let's do that. So again, we have to be given our standard data, our normally distributed data, and we'll say given a mean of 60 and a standard deviation of, let's go with a nice 10. Find the proportion of our data or probability that we will receive. I'm going to go with proportion of our data. Let's go with a between. So how about between, I don't want 70. How about between 55 and 78? So let's say, for example, we're again producing something, and that's a fairly large standard deviation for production, but that's okay. It could be, say we're producing cantaloupe, and the circumference of our cantaloupes average 60 centimeters with a standard deviation of 10 centimeters. Those cantaloupes have a pretty good range of size, but the company that's buying some of our cantaloupes, it only wants to buy ones that are between 55 centimeters and 78 centimeters. It doesn't want the ones that are too small, but if they're too big, it doesn't fit in their packaging. So they only want ones that are between 55 centimeters in circumference and 78 centimeters in circumference. Well, what proportion of our cantaloupe can we sell to them? I'd want to know that. This is what allows us to find that. If that gives you some context on why we might care about doing something like this. So I'm going to give you some time to play with that and try to decide what that proportion is. I have no idea what the circumference of a cantaloupe is, by the way. $1.5. Those the 0.5 and the 0.8 I like, but I think it should be 0.05 and 1.8. So I don't know why those both are one higher than they should be. Because if that's 60, then this would be, and the standard deviation is 10, then that's 50, 40, 30, 70, 80, and 90. So 78 should be less than 2. 78 should be less than 2. 1.8 seems reasonable, but 2.8 would be too far. That would be closer to 90. And 55 should be halfway there. So 55 should be half. So I'm not sure why those are one higher than they should be. Not enough coffee? That happens. But I like that your first step was, well, find the z-scores. It's absolutely your first step. Blame Andrea. It's reasonable. Oh, I got nothing. 18 over 10. So 1.8. Now, where are you going to get a z-score table? Again, there's one in your book. You could Google it. There's one on my website. You can look at this one, but now it's gone. Yeah, if you go to the math department website under me, and then 243, there's a z-score table there. But yeah, you can just Google one too. And again, your book has a bunch of them, so there is no shortage of z-score tables in our world. But negative 0.5 would give us that one. 1.8 would give us that one. So 9641. And 38.5. Now I'm going to write those a little more particularly here. The probability of our z-score being less than negative 0.5 is that, and the probability of our z-score being less than 1.8 is that, just to give you some notation to hang on to. And then Alan, you're saying subtraction. So the probability that our z is less than 1.8, subtract the probability of our z being less than negative 0.5 will give us the probability of being between negative 0.5 and 1.8. Absolutely. So our 0.9641 minus our 0.3085 is going to be what, 68-ish, 67 something. You can tell me what the ish is when you find it. Anybody find that ish? Alan says Olivia knows where it is. What is it, Olivia?
One second, almost there. 0.6556.
0.6556. That seems reasonable. So the idea that this big proportion in here is more than 60%. So what percentage of our cantaloupes will fall within the requirements for these people buying our cantaloupes? Over 65%, over 65.5% of our cantaloupes will fall under the guidelines for this company. We'll have to find a way to sell the really small ones and the really big ones, but we can do that. So say we produced an average of 100,000 cantaloupes every year. How many cantaloupes are these people going to buy? Well, 65.56% of the 100,000 cantaloupes. That's how much we'll have to sell them on average. Does that seem reasonable?
Yeah.
Almost more importantly, does that seem useful? This is
Yeah, it was helpful to try to learn that on our own.
This is one of those
kind
things
of
that you get used a lot out in the world. There is one thing I want to show you before we are done today, and this is almost the part that's going to make it ugly, but I do want you to see it before you go today. I don't want to kind of have it surprise you when it comes up. I think it's like question 3 on the homework. So it's going to come up, fairly quickly. Let's say, for sake of argument, we're told that this section is 42% of our whole. So we're told that proportion. In all these other problems, we've been asked to find a proportion. Sometimes we're going to be given the proportion. So the proportion of our z-scores that are less than some value here, we're going to call C, we're told that proportion is 42%. We need to be able to, sorry, I should put that in decimal, say is 0.4200. We need to be able to figure out what that C value is from this. So instead of going from a z-score to a proportion, we need to be able to go both directions. We need to be able to, given a proportion, find the z-score associated with it. Even better, if we were told what the mean and standard deviation was for our data, we should be able to turn this proportion into the value for which 42% is less. So the trick to doing this, it's not terribly difficult, but the trick is to remember we're going from an area to a z-score. So when we go to our chart, we're not looking for a z-score of 0.42. We're looking for a proportion of 0.4200. That means it's going to be one of these values in the field that's going to be 0.422. So we got to go through and find that. Here's 0.3, here's 0.41, 0.416, here's 0.4207, here's anything closer than that? 4207, 4247. This is the closest one. Now, our chart can't do infinitely many values. We'll be able to get more accurate with the computer, but that is the closest proportion to 0.4200 we have, and that is a z-score of negative 0.20. So that happens when C is negative 0.20. Is that right? 0.20? 0.20. And don't really have to put that 0 there, but might as well. So we should be able to go from a proportion to a z-score, just like we went from a z-score to a proportion. Even more, if this is a z-score, we should be able to turn that z-score into a value with our z-score formula. Our z-score formula is x minus x bar over s. So if we know the z-score was negative 0.20, and we know the mean of our data is 10 and the standard deviation is 2, we should be able to back up and solve for that x. Now we do have to remember a little bit of our solving techniques, but multiply both sides by 2. The 2's cancel there. We'll get negative 0.40 equals x minus 10. Add the 10 to both sides, and we'll get x equals, what is that? 9.6. So given our average production at 10 and a standard deviation of 2, 42% of our data is less than a value of 9.6. Yuck. I know. But the nice thing is, keep in mind, it's the same process as what we did before, except before you started with an X, built a z-score, and then took that z-score to your chart and found a proportion. This time we're just going backwards. That proportion will give us a z-score. Our formula will turn that z-score back into a value. So it's just knowing how to do this backwards and forwards. And that does take practice, but we'll practice that. So lots of examples today. Go start playing with this homework. This does get nicer the more we do it, and we will learn some of the computer tools to help us out a bit. They only help a little bit. Anything I can do for you before I let you loose on this today?
Will you be doing a review on Monday for the exam or test or?
Presumably, yes.
Okay.
And then I had a problem on lab 4. I couldn't figure out the formula or how to set up the probability between, or I guess including numbers. I could not figure out how to do that to save my life.
Okay, well, we can certainly take a look at that. In between numbers, I'll have to look.
So it says that estimate the probability that Seattle will have from 5 to 10, including 5 and 10 clear days. Right. Number.
Right, okay. So let me bring up that lab and we can do that. And you said that was for Seattle?
Yes.
Okay, and Seattle was the 24%.
Correct, yeah.
Okay. Bye, Ellen. So, gonna build the table for Seattle. Where's Seattle? Seattle's there. Did you build both the PDF and the PDF?
I did, yes. Let me try and pull that up. Yeah, I've got them both pulled up right here.
Okay, I'm going to use the cumulative one. So, okay, the number of trial. I don't know why I put it up there. Sorry, should have been down here. So equals binomial distribution. So the number of trials or the number of successes, we're going to use that cell, right? Number of trials was the 31 days.
Right.
The probability for Seattle was 0.24, as I recall.
Yes.
And I'm going to make this the cumulative one, so I want the true. Fair? And then go drag that down, and it should turn into ones at the bottom. Awesome. Okay. So this value here is the value from 10 down, right? That's our cumulative value starting at 10. So this is going to be 10 plus 9 plus 8 plus 7 plus 6 plus 5. Fair?
Right.
And you wanted to know between 10 and 5, including 5, right?
Mm-hmm.
So you wanted those. So this includes certainly 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and 0, right?
Right.
Well, we don't want 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and 0. We want to stop at 5. So that means we want to subtract, take away everything from 4 down.
Oh, okay.
Fair? So you'd be taking the 10 down and subtracting the 4 down. Because if you subtract the 5 down, you're going to lose the 5, right?
Oh, gotcha. Okay.
So this cell minus that cell is going to be that asked for probability.
Okay. All right. Thank you.
Sure. It's very common for binomial distributions to need to look at, okay, this is the number I have. Do I need that number or the number before it or after it?
Yeah.
Sometimes you want to look to one side of something.
Okay.
Okay, so you're subtracting cell 4 by cell 10?
So we'll subtract cell 4 from cell 10. Because the cell 10 is going to be bigger.
Mm-hmm.
So that cell minus that cell. And you could just, put that equals this cell minus that cell. And that's our probability.
And I did fill out both of them. So I did the cumulative and then the PDF. I don't remember the term for that one. But I did
the false.
Okay.
And the nice thing is you could have done it with that as well. If you did, you would be going from 10 to 5. So you would just add those up.
You wouldn't include the 5 with that?
Oh, I did. It's just,
Oh.
it doesn't highlight it. It doesn't, yeah. So we could say instead equals the sum from 5 to 10.
To 10. Okay.
And it would be the same number.
Like differentiate those two.
And for the most part, CDF, the cumulative version, is what we'll tend to use more often.
Okay.
But it's nice that it works either way.
Okay, perfect. Well, thank you. I appreciate that.
Sure, no problem at all.
Thank you.
No problem. If something else comes up that you guys need, let me know.
Okay, thank you. I'll see you guys tomorrow.
Okay, thank you.